Thank you. And thanks to Sammy, I now have a little bit of my breath back. Thank you. So this is going to be the first, really, of the technical lectures. Although I know that I gave Carl a set of slides, which I think he said he got through, so I'm assuming that that's the case. So I'll be able to go ahead and do and get through a good chunk of this. There's a lot of slides. Don't get nervous. I don't actually expect to get through all of them necessarily today. This material blends one into the next. We'll just see how far we get all the sense of calibration. I really want you to stop me as frequently as possible. Okay, I mean, the more I'm stopped with questions, the better off that I am. Before I do this, I really like this idea of trying to give you a sense that this is a living field of study. I am giving you an introduction to nuclear physics. Some of you already have had this because you've taken a course with me or with somebody else. Some of you don't, okay? But one of the neat things is that I'm going to be, even if you've taken it before, I'm coming at this completely differently. I'm trying to give you what you need to know in order to understand the fundamentals for this course, which is focused around weapons physics. But I'm going to give you the complete picture from a nuclear physics perspective. Right now, I'm sorry, let me back up from that. I'm going to give you the complete picture as it is taught. It's not complete. Nuclear physics is evolving and changing right now. And the stuff that is at the core of a nuclear weapon at some level is fission. We still do not have a microscopic theory of fission. We have a bunch of empirical models, approximations, that's all. We are right now, in fact, the workshop that I was at beforehand, I was showing my cover slide, was to try to address some of these fundamental lacks in nuclear physics that we have right now, okay? It was an interagency effort. We had folks from not just the NNSA, but from DHS. We had people from the Defense Department, from the Defense Threat Reduction Agency. And then within NNSA, there were several different organizations that were there, the Office of Science. We were all trying to address these fundamental physics things. So often in the midst of these descriptions and the stories that I tell you during these technical lectures, I'm going to reach a point where we don't really have a direct answer. We have what's called an empirical model, something which seems to reproduce what we've observed. That does not have a predictive capability. And that lack of predictive capability underpins all of nuclear weapons science. The truth is, this has been a field that has evolved by experimentation and engineering. The fundamentals aren't quite there. And often when scientists try to teach you this stuff, they soft pedal that, they show you the beautiful or elegant solutions to problems that have been standing for a long time. I'm not going to whitewash this. We understand some general properties, and we're developing the field right now as we go forward. Okay. So, with that, I'm going to start off here. I'm calling this lecture 2. I won't count how I scared the wits out of you with Hawaii as lecture. I call that lecture 0. I'm starting like a good, for geeks amongst you, a good C program on numbering everything starting with 0. Okay. So this is a picture that I gave to Professor Van Bibber to show. Okay. A roller coaster is a system where energy is changed between kinetic and potential. Okay. And he did show this slide, right? Something along these lines. I think that this is something really important to understand because often in physics, we try to create analogies to things that we actually have seen in our everyday life. And that's what I'm going to try to do, even if it sounds really fundamental. Okay? You can have your cart at the top of a hill where it has lots of potential energy and very little kinetic energy, and then it rolls down and it gets to a point where it's got very little potential energy and lots of kinetic energy. These things that when we do this sort of a plot, and now height becomes energy content, we use these sorts of plots all the time. We call them potential energy diagrams. Okay? We use them all the time. Again, the higher up, the more energy is stored. The lower up, less energy is stored. But more likely, if you roll downhill, you've got that energy back in the form of kinetic energy. How does that sit with people? How do you feel about that? It rang somebody's bell. Okay. So this is gravity, and it's something that we're really used to seeing because we live in a world with gravity. Okay, and it's a nice analogy to have. But actually, this is not the force that's operational in any meaningful way in a nucleus. So what force is present meaningfully in the nucleus? Or what force says? Does anybody know from the folks who've taken my course? Don't be shy.
Strong.
The strong force. Absolutely. The strong force, which we're going to get to in a few slides, is what holds the nucleus together. What other force is operational in a nucleus? Coulombic. Who said that? That was great. Coulombic. And in fact, Coulombic, which doesn't mean anything if you're not technical, it means electrostatic and electrodynamic. It's the fact that the protons have charge. That simple feature is what really dominates and dictates the entire story of fission, which is the energy source in an atomic weapon, and it's the initiating source in a thermonuclear weapon. It's not the strong force. The strong force is what's keeping things together. When it falls apart, it's Coulombic that plays a role, or as we would just call it, electromagnetism. Now, the thing about electromagnetism that's different from gravity is that gravity is only attractive. At least that's what we think at this moment. Maybe not entirely true. There may be something that involves forces that involves mass that's repulsive. We don't know. There is this mystery of dark energy. But for a moment, really, I can say, basically, this is the only thing we've proven. That if you have mass, you feel gravity. And the gravitational force is always attractive. Okay? This is not the case with electromagnetism. If I have two charges and they're separated, and they're opposite charges, they will feel an attractive force. Okay? So if they have an attractive force, and they're separated, what will happen over time? Let's say I'm holding these two charges, and now I let go. What's going to happen to them? What's going to happen? Shout out, so good. Thank you. Okay, that hurt. Okay, they're going to slam together. That's going to be what happens. So in this case, because they're separated, would you say that the potential energy is high or low? If they're separated, the potential energy is high, right? When they come together, what would happen to potential energy? One person says 0. Either way, does it get higher or lower? Lower. We transfer some of that potential energy into kinetic energy. That's right. Okay, now here's the part that's different. This looks like gravity. What I just drew up here could have worked for two chunks of matter. Now let's say I've got two chunks of positive charge and they are in ultimate contact with one another. What would you say about the potential energy of this system? Is it high or low? High. Because what will happen if I let the clock run forward, if I let go of these things? Boom, that's potential energy high. Okay? And of course, if they are separated and going apart, what's going to happen? The potential energy is lower once again. Okay? Does the potential energy ever get to 0?
Depends on how you define 0.
And so that's actually, yeah, what a science energy, absolutely. Okay. Yeah, so the potential energy does depend on how I define 0. Actually, you know what? We have some rigorous rules in physics. Generally speaking, we talk about energy as being a positive quantity. If the energy is negative, the system is bound. But within that system, it still would have only positive energy. But again, you're absolutely right. I'm free to set my 0 anywhere. Okay? That's fine. But the truth is, if I want to have, energy is related to the force that's involved. If I want to actually minimize this energy, I would have to separate these charges by an infinite distance. That's when they would be at minimum energy. Okay? So what we could do is write down a rule that tells us what's going on with the potential energy, a mathematical rule, a relationship. And what we say is that the potential energy is inversely proportional to the separation distance and directly proportional to the amount of charge involved. And this is what that looks like. When I use the word directly, that's code. It means that the quantity appears in the same way on both sides of the equation. In this case, it's the numerator. The potential energy, well, it's in the numerator, and the charge is in the numerator. So if I increase the amount of one charge, the potential energy goes up. If I increase both charges, the potential energy goes up even more. But it's inversely proportional to the distance, okay? And that's the denominator there, right? That denominator, as that number goes to 0, the potential energy does what? What happens if I make the distance between the two charges go to 0? It goes towards infinity. As I can bring the distance between charges down, the potential energy goes up. In fact, it diverges. That's a term that we use in math all the time, and I better introduce you to it right up front because I'm going to use it all the time. It diverges. So we are saved by something here. In lecture 1, Professor Fission told you that the nucleus, that the nucleons that are involved have a size that's approximately 1.2 Fermi, roughly speaking. Proton and a neutron is about that big. So I really can't bring these two things any closer than that. Okay, that would be, so if I took two protons and brought them together, they're going to get to about 1.2 Fermi and that's it. Nuclear matter is very incompressible. But nonetheless, that's a very short distance. Okay? And therefore, I could be storing a tremendous amount of energy anytime I bring lots of charge together in one place and lock it in. And that's the key. I do have to lock it in. See, we're now ready to talk about nuclei. So a nucleus is made up of protons and neutrons, right? Protons have positive charge. So in terms of the electromagnetic force that we were just talking about and its stored potential energy, these are the things that count, okay? Neutrons have no charge. So when we bring these together to form, let's say, a uranium nucleus, okay? If it's uranium, then it has 92 protons. And I've squeezed those 92 protons into 7 million billionths of a meter. This is not a natural state. Of course it is a natural state. But if it were just the electromagnetic force, this ain't gonna happen. This is a tremendous amount of stored energy. I'm getting these things in, you know, a bacteria is like 10 to the minus 6 meters, okay? So I've got this thing in at a billion of a bacterial size. I'm compressing 92 positive charges. And yes, right to the point of like this cartoon shows, they're touching. The size of this thing goes like the size of the nucleus, which Professor Van should have shown you, the radius of it would look like this R0 value of 1.2 Fermi times the total number of protons and neutrons, or A, to the 1/3 power. That really is no more than saying that the balls are touching, but they're not compressing. That's all it is. So why don't nuclei fly apart? If it were just the electromagnetic interaction, they would absolutely fly apart. Maybe the deuteron wouldn't, okay? Or the triton. In fact, the triton doesn't even hold itself as a triton for a long time, because that's got 1 proton and 2 neutrons. Deuteron has 1 proton, 1 neutron. But anything with 2 or more, helium on forward, should fall apart. But we already had the answer. It doesn't fly apart because of the other force, the strong nuclear force. And at short ranges, this is very strong. And at really short ranges, it's tremendously strong. But at a really short range, I'm starting to talk about things inside of the protons and neutrons. The protons and neutrons are themselves composite particles. The purposes of this course, that's irrelevant. It's cool, but it's irrelevant. And they're called what? What are they? 210 and 1 m. What do 1 people? Quarks. Okay. The fact that we can't separate out the quarks that make up a proton or a neutron shows you how powerful this force is. If you put enough energy and you try to rip them apart, all you do is create other particles that appear in their place. You just can't do it. And that's good, because if you did, we'd have a bad day. Okay. So this is the little bit of the force that's left outside of each of the protons and neutrons that attracts one proton to another one, or one neutron to another one, or one proton to a neutron. It's that little bit that's left. And that part is what keeps the nucleus together from being electromagnetically flung to pieces. Okay? So without an attractive strong force, nuclei would just fall apart. Okay? How would I express that if I think about one of those potential energy charts that I was talking about before? Well, it would look like this. It's just going up and up and up. Right? As the distance, this is the distance in this direction, the horizontal. As the distance gets smaller, this thing just goes up to infinity, right? By the way, it's not a mathematically correct line. I just drew it with PowerPoint. So if I start to bring things in from the bottom, it's like the cart rolling up the hill. It can start fast, but as it rolls up the hill, its velocity will decrease. And eventually, what will it do? What would that cart do?
Roll back down.
Roll right back down the hill. Thank you very much. That's right. Okay. And any electromagnetic potential energy that you brought in would be liberated. It would come back out again. The nucleus would just fly apart. Okay. So the reason why that doesn't happen, and why we can actually go and form a nucleus that's stable, or at least relatively stable, okay, is that once we get things close enough, this other strong force kicks in between the nucleons, and it keeps the nucleus bound. I think of it as being analogous, I just didn't get a picture at it, to a rubber band gun. You know rubber band guns? Okay. I should have brought a rubber band. That would have scared people in the front row, you know. So, but you know, what you do is you tense the rubber band and you put it behind something that holds it in place, right? That's what my thumb would be the thing that would hold it in place. If I let go of that thing that's holding it in place, it'll fly forward, okay? But if I'm stretching that rubber band back until I get it over the hump of my finger over here, it's not going to work. If I pull this rubber band, it would just plane forward again. You have to get it into this close-in distance in order for this force to kick in. Does that make sense? And really, that's weird. We don't have other forces in nature that behave in this fashion. Gravity and electromagnetism both have that same rule that I wrote up before, which is that the potential energy that you can store in them is equal to one charge, called charge 1, times another charge, charge 2, over distance. Okay? That's what they all look like. And actually, there's a very good reason for that, that again, I don't get to go into, even though I want to talk to you about it. But it's sort of proof that we live in a three-dimensional world. Okay? If the potential energy goes like that, for those of you who have played around with calculus a little bit, the derivative of this would go not like 1 over r, but like 1 over r squared. And that's like the surface area of a sphere. It's kind of the proof that the further you get away, the smaller the surface looks like. And that this all comes out of that idea. So the strong force doesn't act that way. It doesn't kick in until you get very close. And then it becomes very powerful. And here's the part that's really weird. As you get closer, it gets weaker. It's backwards, okay? And for those of you who took the advanced course with me, we didn't even talk about this, and it's called flux tube formation. Yeah, it's kind of a neat thing, but really it just gets weaker. So eventually, if you put the charges right on top, the strong force charges right on top of one another, it gives them flux. It's called asymptotic decay. So what does this mean? This picture that I had before, where you roll up the hill and roll right back down into the hill, has to be modified in some way, but only at short distances. That's what happens. And I've actually exaggerated the effect of it. We call it the strong force. My goodness, what a misnomer it is. The strong force barely holds together uranium. It's barely doing it. It's a little divot. So now if I come in and I have enough energy, I roll uphill and I slow down, but I don't get to zero when I get to the top. I can get trapped. There you have it. That's a nucleus. I bring all those positive charges together, and we get this little divot due to the strong nuclear force. It's really not very much at all. Yes?
Is there a numerical value to like the distance when the strong force starts acting in?
Fantastic question. Is there a numerical value to when the strong force starts kicking in? Yes, and it's remarkably constant. And this means you've stolen some of my thunder from a later slide. Thank you. It's about 5 to 6 Fermi. That's about the size. Okay? Yes, Mitchell. What's a Fermi? Thank you. A very famous Italian physicist who's dead. Besides that, it's 10 to the minus 15 meters. That's sort of the natural length scale for the nucleus. It's about, actually for a nucleon, I should say, it's about a Fermi, 1.2 of that. Okay? That's right. Thank you. So that's sort of, so this doesn't even kick in until you're at about that distance. Now, it's really interesting and exciting to think about why that happens there. And it has to do with some fundamental properties of the strong forcing of the universe that we live in. And you don't have to worry about it. Right now, all that's important to know is that once you get close, this other force kicks in, and you can now store electromagnetic potential energy. That's the magic. Without that divot, it couldn't happen. So the one obvious question that should come to your mind, and it doesn't to anybody who's actually done this study for a long time, is how the hell were these things assembled in the first place? Okay, who drove the carts up the hill? How did we pull all these protons together, 92 of them, to form uranium? And we did. There's lots of uranium. You can make Fiestaware. The glazes on Fiestaware out there. How did we do it? That's a tricky one, yes. But somebody had an idea? Stars. We use stars. Well, how did they do it? Do stars have little midgets that are pushing carts up hills? How did they? You're right, of course. Stars made it. Okay. But how did they do it? I mean, stars actually they barely work. Okay. They really do barely work. I mean, bombs are much more robust than that. Okay. But shorter lived. Really, how little they work. And folks who took 101 with me, just to be clear, you think of the star as this massive engine of power. If I took a piece of stellar core material and I brought it here into this room and managed to keep it confined because it's got all this gravity pushing it in, it would produce less energy from the reactions to power than you do after eating a peanut butter or jelly sandwich, which is what I just ate. Okay? Less than 60 watts. It's barely working. Okay? So stars do it, you're right, but how do they do it? How do they make these things? Supernova. Supernova. Actually, we now know. That's great. Thank you. We'll get back to that because I will include a lecture on astrophysics because it's kind of cool. All right. But the truth is that no, supernova probably don't do this. We now know as of October 17th. Well, actually, humanity knew as of August 17th, but only a small percentage. Now all of us know that it's probably neutron star mergers that do it. Does it? But, and yeah, look, I gave away the hint. Nature's cheap. You put the nucleus together using neutrons, and then you pull a switcheroo later on. That's it. Because you can bring that neutron. What's the charge of a neutron? What is it? 0. I can bring those in. They'll just wander along kind of nicely and do a weird thing that we'll get to later. When they're wandering slowly, they're actually rather big. And they get close enough to a nucleus, they get to within that 5 or 6 Fermi limit, and they just fall in. It's called capture. It's not even really like rolling up a hill. There's no hill to roll up, okay? Because they don't need charge. But you start with it being very few protons, lots of neutrons, and then you pull the switcheroo. You turn a lot of those neutrons into protons. Neutron capture is how we form heavy elements. Neutron capture is how we form radioactivity in reactors. Neutron capture is how we cause fission to occur in a nuclear weapon. It's all about capturing the neutron. And that's easy because it's got no charge. You could call this nature's gift or nature's curse. When you have that neutron, it can just roll into a nucleus without having to overcome any barrier. And that really is kind of the key to all of nuclear energy, whether it's for productive or destructive purposes. By the way, the switcheroo is called beta decay. Okay, it's not called switcheroo. Although, when I was on the chat, I was like, we should have called it switcheroo positive and switcheroo negative, something like that. But you know, nobody has a sense of humor. Yeah.
How does the enrichment or concentration gradient play into this?
How does the enrichment or concentration of uranium play into this? Well, it turns out that all uranium is unstable at some level. It doesn't stay uranium for a long time. Depending on what kind of uranium you have, which is basically how many neutrons it has, it might undergo beta decay and change one of its neutrons into a proton, or one of its protons into a neutron, or it might lose a little chunk of it called an alpha particle. We'll get into that. It's in these slides. Okay. How does enrichment come in? Well, the neutron star mergers that formed all these uraniums, okay, happened a long time ago. When they first happened, it produced most of these uraniums kind of equally. But the one that we need to make a weapon, uranium-235, there's actually some other candidates too, uranium-235 has a shorter lifetime than uranium-238. So over the course of time, it went from being roughly 50-50 to being about 0.7% U-235. And that's not enough for some of our human applications. And so we purposefully increased the amount of U-235 in the uranium sample. Okay? And it's good that you're asking these questions that make me jump ahead to later slides, because then when you see them, this is called cyclical learning, and this is the way to do it. We're going to jump back and forth like this. If I do this all right, then in about 3 of these equivalent lectures, we'll be done. You'll be able to do problems. No, sorry. No, I mean, in about 3 of these lectures, you'll understand all the fundamentals. We can start getting into the interesting stuff, like stockpile stewardship and things like that. Okay? I mean, I love this stuff as people who take my class 1 test, but I am holding myself back by main force of will. We're just going to learn, you know, the facts, man, just the facts. So we'll do more on this later when we learn where uranium comes from, which are neutrons. Okay. All right. So what does this well really look like? It doesn't look quite like the picture I drew with PowerPoint. Instead, it looks like the picture that I drew with my thesis. Okay. Actually, pretty good, right? Looks about the same, sort of. There's a divot. Okay. So the solid line that you see here is hidden by the 0 axis. This solid line is the kind of well that a neutron would see. So a neutron doesn't have the repulsive parts. There's no rev up coming in. It's just flat. Flat. And then really magically at a particular distance, by the way, you're going to say, why you told me 5 to 6 Fermi instead of 10 Fermi. It's because this is actually for a bigger nucleus, which is actually already a bit larger. It's polonium. Okay. We'll get back to polonium later as well. It's great for killing ex-Russian spies, or forgetting the dissertation. So the dashed blue line is what the protons would see. Now, I want you to take a look. Can everyone see that the dashed blue line is not flat, right? It's slightly above the 10 MeV line here, and slightly below it here. Can you see that? The neutron line really is flat. Okay? This little slow slope, that's this piece right here. Okay? This bump is this bump. It's the peak. The truth is that the electromagnetic force has a long range, and it's stretched out. So if I zoom to the top, at the top, this is what it would look like for real. And you'll notice something here. The proton well is boosted, right? It's up a lot. And it is more shallow. So it's boosted up here. This is minus 50. This is minus 30. But if you look here, the gain here is only about 11. So it's actually shallower. There isn't as much of it. It's shifted up and compressed slightly. Why is that the case? What is it about protons that make them different than neutrons? Coulomb repulsion, charge. Protons have charge. So the well isn't quite as deep, okay? And the whole thing is shifted up slightly. That's important. Okay. Now, let's say I want to start filling this up, okay? I start putting neutrons in. This picture, by the way, is actually, what I'm about to do right now will make some people grin and look like, haha, he's doing simplification. It's actually not too bad of a simplification. I want to ask you, as I start putting more, remember blue balls or neutrons, okay? If I start putting more blue balls in here, what will happen to the later blue balls? What will happen? Will they be closer to the top of the well or at the same height? What will happen? What do you think? They're moving up. All those later neutrons, as they come in, because they're not compressible, right? They're filling the well. And that's true. And if I were to go up to the neutrons way up at the top over here, are there more of them at high energy or than there are at lower energy? What do you think? Are there more up here at the same height as there are down here? Yeah, that's right. The same thing. Now, in 101 and 210M, we learned all about 2L plus 1 degeneracies and stuff like that. But this is it. This is basically, and this is kind of a cartoon only in one way. I drew this in one dimension, distance. Last time I checked, our world has 3 of them. And so then things get, and by the way, things move. And so you get this other quantity that comes in called angular momentum. But don't worry about it. Doesn't that feel so good that people who took 101 and 210? You know, schemes, something like that. No, we're all good. Well, eventually I get 1 neutron in there. And what is it going to do? It's now all the way up at the top. It's going to disappear completely. It's rather remarkable. What is it going to do? Well, basically, it's going to wander off. It's not going to roll down the hill because it has no hill to roll down. The hill is for protons only. It's just going to wander off. So once I fill the well, neutrons just fall out. Or actually, we don't like to say fall. We say drip. And that's exactly what we say. So nuclei that have too many neutrons are said to be on the drip line. The too many neutrons, they're on the neutron drip line. They just drip off. That's all it is. Okay? So now, what do you think would be the case if I did this with protons? I won't let you see. Same thing holds, by the way. Lower down, fewer protons, higher energy, more protons. Okay? There's fewer of them. It's a shallower well. And so you're always going to expect there to be fewer protons than neutrons in any nucleus. Okay? And of course, because of that, okay? And will this proton just drip or drift out? Not at all, it'll shoot out, okay? But we still call it drip line because we like this symmetry thing. We can't seem to get over that, okay? But really, it's not dripping, okay? These things shoot out when they come out. It's called proton emission, and it really does happen, okay? So this is the essence of it. Nuclei have more neutrons than protons because of the Coulomb repulsion. The well is what keeps the nucleus together, and the well comes from the strong force. But what is this mysterious strong force? Where does that well come from? Don't worry, I'm not going to get philosophical on you. I'm going to just answer you very pragmatically. It comes from the nucleons themselves. It's the protons and the neutrons that create this well. Okay? In other words, if I have just one particle sitting alone in space, it doesn't make sense to talk about a strong force for that. I need at least two of them. And then when they get close enough, 5 to 6 Fermi, they fill that bond and they come together. There's the well. I need at least two of them. If I have more of them, I get more of a well. It gets deeper and continues. It's a weird well. Don't get me wrong. So if I have two particles with charge interact with one another, it acts like the system is centered at a midpoint. The nuclear force doesn't do that. Okay, it's kind of weird. Yeah, it actually has like this off-centered nature to it, which we call non-centrality in physics. But really, overall, it's just the more of them I have, the deeper the well. That's the way it works, until the well gets so large that, well, something happens. And that's what we'll talk about a few slides down. So as we add more nucleons, the well gets deeper, and right to the question you asked, until the nucleons on either side of the well are about 5 to 6 Fermi apart. That's it. That's the strong force. Strong force, short range. Big strong force, short range. Okay? That's it. 5 to 6 Fermi. Really constant, by the way. Really doesn't deviate very much from that. We don't have a good trick to affect this, which shouldn't surprise you at the end, like, can I have gravity? You know, not really, I can bring more matter together, but that's about it. With gravity, I can, of course, compress things and make them denser. I can't even do that with nucleons. If I push nucleons hard, they don't really get any closer to one another. If I push them really hard with, let's say, gravity, I can actually make a thing called a neutron star, but basically that's just one big nucleus. It's got the density of a normal nucleus. If I try to push any harder, it resists it until it gives up. And then what do we get? Does anybody know what we get if I actually try to compress things more? Black hole. That's it. And it all comes back to actual physics at some point, right? So the range of the strong force sets a bound on how large we can make the nucleus. A nucleus can have more neutrons than protons, right? Because it's got that deeper well. So one of the things I like to do is create a plot of the number of protons in the y direction versus the number of neutrons in the x direction. And now every isotope, every combination of protons and neutrons that we call a nucleus can fit somewhere on this. And this will not be at a 45-degree angle. It will favor the neutron number. And we get something that looks like this. And this is what we call the chart of the nuclides. Any combination of protons and neutrons that we know of has a home on this chart. There are ones that exist that we do not know of that do not have a home on this chart, because this is a chart of empirical data. The chart of the nuclides, which is something that we use every day in the practice of applied nuclear science and basic nuclear science, is basically a graphical library. You're looking at where all nuclear data information is stored. Every point here represents a nucleus with a particular property. Is the nucleus stable? If it is, we give it the, well, raise your hand if you're colorblind. It's okay, okay. Yeah, and we really, by the way, at some level, almost all men are a little colorblind. We're all, you know, we're mutants. This dark hue over here, it's good working with Carl, because he gives me training for this. This dark black here is black. These are the stable nuclei. Stable is a relative term, but as far as we know, the vast majority of them, especially up right up until this breakpoint up here, which we'll discuss later, really are stable. Like they live, as far as we know, forever, which disturbs me, but for different reasons. As we go off of this black line, in either direction, you begin to see that there are different colors. That's because those nuclei have different lifetimes. This particular way of showing you all we know about nuclei, the color scheme that's in this is there to indicate length of lifetime, how long that nucleus exists, on average, until half of them in a given ensemble have decayed away. That's called a half-life. That's something that used to be taught in class. I'm not going to teach. I don't think that it's essential here. We're going to focus on other things. So what I am going to expect you to know is how to retrieve information from a chart of the nuclides, and in particular, the one that we have at the National Nuclear Data Center at Brookhaven Lab. And actually, I will send around another one as well, an equally useful, it's actually aesthetically, I think, less pleasing, but actually has more utility, is something called Live Chart, which is maintained by the International Atomic Energy Agency. And it gives you all of the properties that we know of all of these nuclei. How long they live, well, obviously, first of all, how many protons and neutrons they have, how long they live, what their mass is, and that's what we're going to get into next. And that's very important, okay? And what kind of state you can find them in. Sometimes you find them with no internal energy. Sometimes they have some internal energy. Okay, you can think of that as heat. You can heat them up, and they have a certain amount of internal energy. All of that information is accessible there. You can bring this chart up. If there's chart of nucleus in the corner, you click on it. You can go move around to any one of these points and click and bring in all these properties. It's all there. All brought to you by your tax dollars at work. Actually, at this point now, we're no longer your tax. It's probably about 40% of your tax dollars and about 60% of the efforts of international nuclear data evaluators who coordinate this effort with us through the IAEA. So another thing happens when we assemble nuclei, okay? So let's start with 2 protons and 2 neutrons. We have the masses of these particles. The proton mass is 1.673 times 10 to the minus 27 kilograms. The neutron is 1.675 times 10 to the minus 27 kilograms. So I've underlined and italicized that just to bring attention to that. Note that they're not exactly the same. They're close, but they're not exactly the same. The neutrons have slightly more mass. So when we bring them together, we get a helium nucleus. And that helium nucleus, if I just combine these numbers, I get 3.696 times 10 to the minus 27 kilograms. Okay? If I look, though, at a helium nucleus, which is an assembled set of these, I get 6.685 times 10 to the minus 27 kilograms. This is it. We measured the mass actually of these particles incredibly precisely. Okay? What's happening? Mass disappeared. Now, this part is tricky because we associate mass with things. Chalk. That must be okay. Whatever. Me. Erasers. So it's true. Things have mass. Some things have mass. Some things don't. But actually, when we assemble things, again, with an attractive force involved, okay? I mean, this is attractive. So at the end of the day, at some point, these particles could rush together with energy. What you end up with has less mass. Some of the energy that you got out of assembling 2 protons and 2 neutrons into a helium have gone away. The mass has gone away because the energy was released. Assembling helium-4 from 2 protons and 2 neutrons results in a mass loss of about 1.1 times 10 to the minus 29 kilograms. Okay, that's what happens.
Well, you have a missing factor too there on the left.
Oh, I do I?
Yeah.
You're right, I'm sorry.
That number should be.
It should be twice as big. You're absolutely right. You're absolutely right. Yeah, thank you. It's all corrected on the slides. Thank you. But there is a destruction of mass that occurs. It's small, but it's present. And this I just took from Carl because I thought it was cute. Because you have to have at least one picture of Einstein if you're going to have any sort of discussion. Okay, mass can be converted into energy. Okay, and yes, that's it, right? I went through and just kept throwing different factors together. Okay, so we define this binding energy quantity as how much mass is lost when the nucleus is formed. So we can look at the different composite particles before we bring them together, and then we look at the sum particle after it's been brought together. Okay. So if we look here, it's just done like this. This is the mathematical notation. If I sum over all of the initial particles minus the sum of all the final particles, I get the binding energy. Okay. It's the energy, this mass is turned into energy, which is liberated. The assembly of 2 protons and 2 neutrons into an alpha particle releases energy, actually rather a lot. In fact, per nucleon, it does more, I think, if this is true, that assembly than any other assembly of 4 particles that you could do at any point in time in the nucleus, if you're assembling a nucleus. You never get any better than this. It's the most bound system that you can have per 4 nucleons. Okay. So we have to have a mass unit because we don't want to carry around all of those big 10 to the minus 29 numbers and stuff like that. So our favorite mass unit in nuclear physics is the atomic mass unit, which seems like it should be the favorite unit of measure in atomic physics and not nuclear. Okay. So 1 AMU is 1.67377 times 10 to the minus 24 grams. It's actually even better known than that. Okay. And mass in AMU is a pure number. And the way it's defined is relative to carbon-12, because that's a ubiquitous thing that we can find in any lab, almost anywhere here on Earth. Carbon-12, which is basically, by the way, 3 alpha particles, if you give it that way, 3 helium-4 nuclei, is defined as having a mass of 12.00000, all the way on up forever. Okay. So 1 atomic mass unit is defined to be 1/12 of the mass of a carbon atom. And note that that does include 6 electrons as well. By the way, a little side note here about electrons. We haven't really discussed them up to this point because they're not part of the nucleus, but they're there. They equalize out the charge that we have in the proton. And one interesting thing about an electron is that I can't write an equation like this up for one. As far as we know, electrons have no size. Okay, there is no spatial extent of them. And we've really gone very far to try to figure that out. Okay. They're just points of charge with very little mass, but they do have mass. Okay. So to give you an idea about what this looks like for other particles, hydrogen 1, also known as a proton with an electron, is 1.00725. And you can read the rest of the numbers out. There's the mass of the helium. There's oxygen 16. You'll notice that a lot of the most familiar elements that we have that make up life on Earth are groups of alpha particles all around here. Carbon is 3 of them. Oxygen 16, which is the most common isotope of oxygen, is 4 of them. Okay. So the binding energy is just the number, the proton number times the mass of hydrogen plus the neutron number times the mass of the neutron minus the assembled mass of the assembled nucleus. That's the binding energy. So what happens basically is that as you bring together Z protons and N neutrons, you end up with something that has manifestly less mass. And that mass is an energy source as you assemble up to a point. So what would happen, remember back when I was filling that neutron well, if I drop a neutron in and I'm already up at the drip line, am I going to decrease the mass of that system? So if I'm all the way filled to the rim, will that last neutron go in? Will it? No, it'll just drip off. It might go in momentarily and fall right out. The mass will not decrease. Okay? There has to be some space in the nucleus to allow that to happen. So what does this mean? It means that as you combine things, you can actually liberate out energy if you combine protons and neutrons, okay? And so here is the energy that we would associate with the proton mass. It's 938.272 MeV, okay? That's what it is. If I turned all of the proton mass into energy, this is what I would get. I get a bit more for the neutrons because the neutrons do have higher mass, okay? And there's what it is for an electron, about 1/2000 of the value of the proton or the neutron. So what we often do, for a given nucleus, we tend to know, obviously, what its number of protons and neutrons there are. So what we like to do is define a quantity called the mass excess. And what the mass excess is it's the actual mass of the assembled nucleus, however many protons and neutrons you've got, minus A, the total number of nucleons, times is MuC squared. Mu is that atomic mass unit times C squared. It's the difference between what the energy of the nucleons are when they're separate, combined with the energies when they're pulled all together. Okay? Now, once I know that I can change the energy of the system by binding of the nuclear system by binding more protons and neutrons together, I can define a quantity called the Q value. So Q value represents the energy release or the energy consumption that takes place in the assembly of a nucleus or the disassembly of a nucleus. It is basically an energy loss or gain term. So the example that we're looking at here is one that was actually used in the first nuclear weapon. Actually, the first nuclear device. Okay, in the Trinity Test, we used alpha particles being made incident on beryllium to create, that shouldn't be a P, that should be a right arrow. What we needed was a P. Wow, how did you do that? That's kind of fun, okay? That's a right arrow. Okay. Alpha plus beryllium-9 goes to carbon-12 plus a neutron. This particular device, this alpha particle, this helium-4, came from the decay of a nucleus called polonium. Okay? And the polonium on beryllium reaction can produce neutrons, which was something that was needed to initiate the fission chain in that device. So I can calculate the Q for this reaction by taking the mass of the helium-4 that came in, plus the mass of the beryllium-9 that came in, and subtracting away the mass of the carbon-12 that came out, and the mass of the neutron. Again, in any of these nuclear reactions, proton and neutron number stays the same. I'm not destroying particles. I'm just combining them and some mass goes away. If you want to think of it this way, the carbon-12 protons and neutrons actually have less mass than when they were free. Okay, they've lost some of their mass individually. Each one has become a bit smaller. And actually, they haven't become any smaller. I guess you see their density has gone down. Something like that's what I think of it. Okay, so you can plug in these numbers. You can get these numbers from the National Nuclear Data Center or from a table. You can do the math, and hopefully you do it right, and you end up with 5.7 MeV. So this kind of a reaction is called by scientists exothermic. It actually releases energy. That's the, and the real reason why, by the way, that happens is going to be clear. Because remember I said that this helium-4 nugget is a really tightly bound, excellent nugget of nuclear matter. Okay? So what happens in this reaction is I bring one helium-4 together with two helium-4s that have a little neutron doing a dance between them. That's what beryllium-9 is. Okay? It's there's a number of these nuclei where we found where that one extra particle is providing the binding. Beryllium is as a nucleus is barely holding it together. It's really easy to break beryllium. We actually don't have good mechanisms for its production, but we're entirely sure it exists. So what happens here is that I go from two weakly bound helium-4s in here and one out here to three tightly bound ones. And that gives me 5.7 MeV. So if I have this binding energy quantity for a given nucleus, or for a set of nuclei that have given masses, I can make a curve. And the curve would be the binding energy, again, the difference between the mass of the assembled nucleus versus the separate nucleons, versus the number of nucleons. And this is called the curve of binding energy. And this is what it looks like. This is actually, by the way, the binding energy per nucleon. If not, this thing would just keep traveling straight up, right? You just keep adding more binding energy in. But the binding energy per nucleon shows you how well bound a given nucleus is. And what you see right here is that there is a huge surge going from the smallest nucleus, which I guess I don't really know if you can call a proton or a neutron nucleus, but if you could, going from that up to mass 4, which is that alpha particle of helium-4, I get a huge amount of energy. I climb most of the way up this curve just from doing that. Most nuclear reactions that occur, and I'd say virtually all that occur in nature, end up bringing us somewhere near the formation of an alpha particle. Okay? Because there's so much gain in binding energy, or so much mass lost when you pull that together. It's freed up, it's made available in some other form. Kinetic energy, radiation, it comes out. It's there as an energy source. Okay? If I keep adding more nucleons on helium-4, I get another big jump in stability, and that happens at carbon-12. And then I get a smaller one, and that happens at oxygen-16. And then neon-20, and et cetera, et cetera, et cetera. And eventually, somewhere around nickel-56, iron-56, nickel-62, nickel-58, this iron-nickel group, we begin to reach a point where we have the greatest amount of energy released in assembling nuclei of that size. Okay? That's the point where you get the most energy out. It's the peak of the curve. Now, that doesn't mean I can't keep adding more protons and neutrons on. The nuclear force is still attractive. It's just becoming a little bit less attractive. I'm getting towards the top of the well. And when I get towards the top of the well depth is less. Again, if you know some calculus, okay, all this is the well goes like the derivative of the potential. And so what's happening is you're beginning to reach the point where that derivative is getting smaller. The force is the force rather than you're feeling. It goes like the derivative of the potential. And that force is becoming less. You really are getting less of it out there. Okay? You can keep doing this right up to some point. Now, in nature, that point basically is effectively uranium-238. Uranium-238 is the nucleus that we find in nature, almost, okay, that is most massive. That's the top, okay? Now, could we add more? Yes. In fact, people did. Glenn Seaborg went ahead and started making heavier elements, okay? Starting with plutonium and moving up from there, okay? So you can do it, but it turns out that those elements, why don't we have them in nature? Why don't I have plutonium? Why can't I go to a plutonium mine and mine plutonium directly? I can't, by the way. Any guess? Come on.
They decay away.
They decay away. They're too short-lived. They were there. When they were made in the neutron star mergers, we had plutonium, californium, curium, berkelium, probably things well beyond the points of livermorium, deuterium, and nihonium, the heaviest ones that we made. They were all made, but they all decayed away. And actually, the most likely thing they did out there was little bits and pieces of them fell off, called alpha particles, and we'll talk about that. But that's it. We reached sort of this maximum. The one exception, by the way, to the rule, there is actually a tiny amount of naturally occurring plutonium-244. There is a minuscule amount of it. it's used by for certain geochronological applications. But really, you would need 238. That's the end of the story. Okay. So let's say, so you see that this is the most bound nucleus per nucleon. So I gain energy by adding nucleons up to this point. If I start with a heavy nucleus and I subtract nucleons out, I also gain energy. Both directions that move me towards the top of this would release energy. So if I zoom in at the top of this curve, this is what you'd see. So I've done this trick called, notice here, back in this picture, it goes down to 0. Here, I'm only going to about 7.5. Okay, that's what we call zero suppressed. We're going to see a lot of people do horrible things with statistics by showing zero suppressed plots and not acknowledging that. Okay, but now you can see a bit more of the structure right around the top. Fusion combines light nuclei and brings you up towards this maximum of the binding energy curve. Fission breaks up nuclei and brings you towards the top of the binding energy curve. Both of them are accomplishing the same thing. They are bringing you into a situation where the protons and neutrons that form that nucleus have the least mass individually. They're the most bound and they release the most energy. So what this means actually is that, and this all, everything that I'm showing you here on this plot are stable nuclei, okay? These are all nuclei that we find in nature. There are lots of other nuclei that we can find that do not have that characteristic of stability, but rather they undergo decay. And in that case, I could go to those and I could calculate a binding energy. I could take the mass of that unstable nucleus, subtract away Z times the mass of the hydrogens, N times the mass of the neutrons. I can end up with a mass defect. I can tell you how much. It's still a bound nucleus, but it's not as bound as a stable nucleus. So you can think of these stable nuclei. I mean, you draw it as a peak here, but I could turn this whole thing upside down. And you can think of it instead as being like a valley. Nucleons that have this stability feature are the most bound. And they form the bottom of a valley. And so if you were to think of that chart of the nuclides, this black strip here of the stable nuclei is kind of like the bottom of a valley. In this particular case, there's a picture that Carl had about Moab Rim in Utah, okay? Which I guess looks like the chart of the nuclides. I don't know. Okay. Well, he chose that. Okay. So the most bound nucleus for a given mass is the stable one, right? Running down the middle. But I can have unstable ones on either side. Where if I actually took a nucleus on one of those points and allowed it to change some of its protons into neutrons or neutrons into protons, it would become more stable until eventually it reached complete stability. That's the black one. So let's look at two lines in this chart of the nuclides with a fixed mass number, which means that all the nuclei along this line have a total mass number of 140. This could be 70 protons, 70 neutrons. It could be, well, it won't be, I don't know if we'll go this far. Probably not, but it could be, say, 50 protons, okay? We'll have that 50 protons and 90 neutrons, 2, 140. Not stable, but it would be there. So let's just go here and slice across here. And let's look at all nuclei that have 140 protons and neutrons, okay? All the ones that we know. Not all of them, but just all the ones that we know. And I'm going to do another thing. I'm going to plot this with increasing energy in the y direction. This is what it looks like for mass 140. Okay? The bottom of the valley is cerium 140. Cerium 140, we thought I said Siri. Are you scared? You should be scared. So this way you can't have the 140. Okay. That's the most stable. And look here, here's the chart. That's 0. We're defining that as 0. And then it goes up from there. You can see that like xenon 140, and I don't know what one responds to it. It's xenon. Okay. Xenon 140 has 15 MeV that could be released. If it just went through the process of turning 4 of its neutrons into protons, it could release 15 MeV. I could look over here instead and look at europium 140. Okay, and I can see how much energy is released there. This is what that valley looks like. So we look at A equals 140. One quick distinction that I can make is between nuclei that have an even number of protons and neutrons, which I've circled in red, and those that have an odd number of protons and neutrons. Because it's an even number, it's got to be either even and even or odd and odd. That's it. Okay, and there they are. And what you notice right away is that the one with even is the bottom. Remember that. That's important later. Okay. Now let's look at 141. I'm just moving to the next chain over. So now I can have an even number of protons and an odd number of neutrons, or an odd number of protons and an even number of neutrons. So in this particular case, first of all, you go back to the previous plot, you see that really decidedly cerium 140 just drops. It's the bottom. Everything right around it is about the same. But when you get to that cerium 140, it really drops all the way down to the bottom. Here, it's a little bit more competitive between the two options that you have. The odd Z praseodymium and the even Z CE. Okay? These are the two options that we have. So I can gain additional binding energy per nucleon by turning a proton into a neutron or a neutron into a proton, depending on which side of this valley I'm on. So remember what I said when I said that nuclei are assembled as neutrons and then become protons? Yeah, this is how that happens. Okay? So we can give an example here of one of these. Okay? It's called beta decay. And it moves nuclei, in this case, one square up in proton number and one square to the left in neutron number. Just like that. That process can occur. It will turn carbon-14 into stable nitrogen-14. It's kind of a neat example to stick with. Carbon-14, as many of you may know, is something that we use for carbon dating. Okay, we're determining the age of things that have a lifetime on the order of, I guess it's 6,700 years, 5,700 years. Here we go. Okay. The whole idea there is that there's always a little bit of radioactive carbon in the air around us. It's being created continually by the fact that we have the Earth's atmosphere being bombarded with radiation from space. You bring that in either by breathing it in or by eating it. And then at some point you stop breathing and eating. And then whatever carbon-14 you have decays away. So beta decay involves turning, in this particular case, right, I'm turning carbon-14 into nitrogen-14. This is 6 proton system into 7 proton systems. Okay, that's what I do here. But it's not just that I get to flip a particle. Right away, you should know I shouldn't be able to do that because we believe that charge is a constant quantity. Okay? So what has to happen instead is I've got to produce something else with the opposite charge that frees itself up. Okay? Actually, I'm going to go out of order slightly. Let me do it here. So this is what this decay looks like. You go from carbon-14 to nitrogen-14. You've increased the proton number by 1. So you've got one more positive charge. That means that you have to have a negative charge. Okay? The simplest negative charge you can have is the electron. So it creates an electron. Now, as it turns out, that's not the end of the story. Another particle is created as well. It's called an antineutrino, and that will be clear in a moment why. Okay? The way that we figured this out is because when we looked at the energies of these particles coming out, they indicated that there were 3 particles coming out. Now, what do I mean by indicated that there are 3 particles coming out? This. So if I have a big medicine ball, I'm not actually going to ever do this trick, and I'm holding it to my chest, and I was standing on slippery ice. This would be completely outruled in any natural laboratory that you could ever do. Here we go. And I pushed this ball this way, what would happen with me? Fly back the other way, absolutely. And in fact, if that ball had the same mass as me, and I was holding it like this, I'd be having back problems. But if I did that, the velocity which the ball left with, I would go backwards with the same velocity. This is something that fundamentally in nuclear physics we call conservation of momentum. Don't worry about that in a moment, not essential. Okay? But that should be relatively intuitive to you, that that would be the case. If that ball had half my mass, and I pushed it away, then I would recoil with half the velocity. Okay? That's because there are only 2 things involved in this: the ball and the lid. Now, what if, instead of that, I was arm in arm with Sammy, and we were both holding onto this thing, and at the same time, we both pushed, okay, and on this ball, and we unlinked arms at the same time. Well, let's say that I was the last one to eat a hearty breakfast, and I've got more energy that day than Sammy, then I'm going to push a bit harder. I might recoil a bit more. On the other hand, it might be that I just injured my back holding a ball that's about the same mass as me, and Sammy's younger and in better shape. She pushes the ball, and now she's going to end up recoiling more. Any given time, a different outcome might happen. And so the energy can be shared differently between the 3 particles. And this is what we see in beta decay. If we look at the energy of this electron coming out, which we call the beta particle, it has a broad range. Okay? Sometimes it has a lot of energy, sometimes it has less energy. Meaning that the amount that's left in the recoiling product nucleus, in this amorphous thing called the antineutrino, okay, varies as well. So we know, based on seeing the energy of the electron, which we've done, the fact that it isn't just a single value, like it would be if it was just me and the ball, means that there are 3 things. It's what's called a 3-body final state. In general, if you see that shape, you know that something's going on like this. And it was through this observation that Enrico Fermi, who was short but taller than 1.2 Fermis, determined that there was such a beast as a neutrino. There had to be another particle involved, because if it was just the electron and the recoiling daughter nucleus, it would be 1 value. That's it. Okay? So that was the evidence that there. Actually, we are now, this particle is really a quite amazing particle. Neutrino means little neutral one. It has no charge, and it basically doesn't interact hardly at all. Okay? So if I shot a neutrino down into the Earth right now, it would almost certainly leave the other side having ignored the Earth. Okay? It's that weakly interactive. That's really quite interesting, but believe it or not, we're now using neutrino observation to track reactor function. We're just very patient, okay, and we can actually track this. And I'll talk about that possibly later on in the course. We'll see if time permits. Let me just go back here a bit more on this topic. We're almost done. I think this is a good place. We got actually quite far, which was terrific. Okay. In beta decay, the mass stays the same. In this case, the Z goes up by 1. For our purposes, you can think of that neutrino or antineutrino as having no rest mass. Again, it's a shear of energies that comes out. And it's important across the whole chart of the nuclide because it allows us to move down these values, changing protons into neutrons or neutrons into protons. And so, of course, if I am going to talk about it going both ways, okay, nuclei that have too many protons, they can undergo a kind of beta decay as well. No great surprise. Okay, it's beta minus decay. You go 1 square down and 1 square to the right. Okay, here's an example of nitrogen 13 going to carbon 13, and then everything else is the same. Okay, it really is basically the mirror process. The point to note here is that this beta plus particle that comes out is what's called an anti-electron. Okay. So it's a way that a nucleus can lose some of its positive charge. It sends it out in the form of this anti-electron. Now, why is that important? Why am I stressing this? That anti-electron, if it were to encounter an electron, would annihilate the other particle and immediately release the mass is the form of energy. Antimatter is indeed, as far as we can tell, just this reciprocal kind of mirror image of regular matter. Okay? And this is by far the densest form of energy release that you can have. Yes?
What do you mean by the energy is not sharp, but it's sheer?
A shear? That's a technical term, a shear. Okay. This picture, it's a broad range of energies. That's what I mean. That's a good question. That's what I mean, as opposed to that technical term, a shear. Okay. So it's important that just to keep in mind, we're going to talk about some of the most lethal devices that humanity has ever created. Okay? Nuclear weapons liberate this small amount of binding energy. Okay? And can wreak havoc with them. But antimatter, that's the highest form of energy that you can have. And by the way, it doesn't have to have opposite charges. There are anti-neutrons. And if they encounter neutrons, they will annihilate. Okay, and release up 2 neutron masses worth of energy completely. Okay, it's a very small mass loss when you assemble a nucleus. When you bring a piece of matter and a piece of complementary antimatter together, you release all of the energy, right? And we all know this is a great thing to end on, I guess, right? The antimatter is going to blow Captain. Raise your hand if you know who that man is. Wow, amazing. How about Jordy LaForge? Raise your hand if you know who Jordy LaForge is. A few more hands. I really don't know anything beyond that, which dates me. This is called Star Trek. This is on the test. Okay. So antimatter is the densest form of energy. And we do produce it in copious quantities through beta plus decay. And we can look then for signs of this, which is this energy being liberated. And it's 2 pieces of energy that have the same mass energy equivalence as the electron. And that will be important later. Okay, so we're almost done. There's one more bit of decay that I'm going to cover, and then we're going to be into fission that fast. Okay. There's been a bit of interaction, which is good. Any questions? So for those of you who took 101 and 210M with me, really, and stayed, thank you. Okay, I appreciate that. You want to get a sense of what I'm saying when you're working in groups. For the rest of you, I hope that this didn't run too fast. At some level, I will tell you, I cover topics here in this one lecture that take me weeks to get up to in the regular nuclear physics course that I teach. But I think you can get there. I think it's understandable at this level, and it will allow us to move on to the fun stuff. Okay? Although I think this is fun stuff. All right. Thank you. So we're going to share the next lecture. So on Wednesday, we'll continue. We'll take up right after Scotty. By the way, his name is Montgomery Scott. That's Scotty. That's the real Scotty.